Hello everyone, and welcome to the Getting Started course for structural topics in Ansys Discovery. In this course, we'll be reviewing several structural features and capabilities within Discovery. By the end of this course, you'll be able to perform various basic analyses while exploring your design possibilities. We'll get started by importing the model. Let's first launch Ansys Discovery. When open, we can click on the Browse button to open our file. Let's browse and open the aircraft engine mount assembly file that we will be reviewing. Simply click on Browse and open the file. By default, you will be in your current working directory. You may select the file from here or navigate towards the Browse option to choose a different directory and file. Let's select our file and get started. Now that the geometry is imported, we can begin to review the assembly. As you can see, the aircraft engine mount assembly includes all parts from the engine to the wing profile. We will be interested in the mechanical performance of the mounts. Therefore, we will omit the aircraft structure components and we'll idealize the engine as a lumped force. So first, let's get started by analyzing a single part. We'll select the upper mount for this example. To do so, we must select the part of interest and hide and exclude all other parts from the simulation. We can do this by navigating towards the geometry tree and clicking on the drop-down arrow. By default, every solid part that's imported into Discovery will be included in the physics simulation. This can be noted by the left column, which shows the simulation status. The second column shows the visibility status. Both can be toggled on or off by clicking on the icons. Since we'll be focusing on the upper mounts, we can select all other parts in the tree and exclude them from the simulation. We'll hide them as well. Now that we have reduced the scope of our simulation to the upper mount, we can begin to set up our physics conditions. We'll need to switch to the Simulation tab, where we will be able to perform and access all simulation-related actions and tools. We will begin by assigning a material to the upper mount. In the ribbon, click the Materials button and then select the upper mount. You'll then be able to update the material and view the material properties. For this example, we'll assign structural steel. Now double-click Escape to exit the Material tool. Next, we'll begin to assign boundary conditions. Let's start by assigning structural support. In the ribbon, click the Structural button and select Support. Note that you can always access physics tools through the halo as well. The upper mount is supported at these three regions. We'll want to change the support type from fixed to hinge, since this will be the type of constraint experienced at these locations. To do so, click on the drop-down arrow and select Hinged. Now, click Accept or hit Enter. We'll continue to do this for the two remaining locations. Note that for hinge supports, you can select multiple holes, but they must be concentric. When finished, double-click Escape to exit the tool. Let's continue and apply some loads on the mount. We'll be simulating the thrust from the engine and a side load. Let's start with the thrust force. Recall that we will idealize the engine thrust as a remote load. We'll assume a remote point at the engine's center of mass. To calculate the center of mass of the body, switch to the Measure tab. Click on the Mass Properties button, and then select the engine. Note that you can select the part in the geometry tree, or you can show the part and select the 3D body. We'll approximate the center of mass to 1,287 millimeters in the X direction and 0 millimeters in the Y and Z directions. Click Escape to exit the tool. Now, let's return to the Simulation tab and click on the Structural button. This time, we'll select Force. We'll want to select the forward and aft mount attachments for the load application. There are several holes, so let's use the Power Select tool. Navigate towards the bottom of the window where you will see the Power Selection tool. Click on it and select one of the smaller attachment holes. You'll notice after clicking various selection options will appear. Let's select holes equal to 12 millimeters. All attachment holes will then be selected and we'll just need to select the 3 larger forward holes manually. You can exit the Power Selection tool. Notice that next to this tool is the Name Selection tool, where you can save selections like this one for future use. Additionally, if you accidentally alter your selection, you can restore it by clicking on the Revert Selection button. At this point, you can use the Guide tool to set the direction of the force by either selecting a curve to align to or selecting a face to be normal to. You can also set the direction by using force components, as we'll do now. On the right side of the HUD, click on Use Force Components, and let's enter a negative 1,000 pound load to orient it towards the forward direction. Note that you can enter a value with non-default units, and note that you can change the default units in settings. Now, click on Use Remote Point to enter the remote point of the load. We'll enter the center of mass calculated earlier, which was 1,287 millimeters in the X direction and 0 millimeters in the Y and Z directions. Now, click Enter to create the remote force. Next, we can apply the side load. Double-click Escape to exit the tool. We'll model the side load as an acceleration load on the mount. This time, let's access the structural tool through the halo, and let's activate the interactive menu as well. First, let's click on the halo and navigate towards the structural tool, and then select the acceleration option. Now let's activate the help menu by clicking on the help button on the upper right corner or by clicking F1. Let's simply follow the steps to assign the load. We'll select our body and keep the default orientation in this case. We'll specify a 3G load in the local Y direction, and we'll let the other directions be free to move. Note that if your coordinate system is oriented differently, you can adjust it by clicking on the direction tool guide or holding Alt and then clicking on the guiding geometry, which will align the local X direction. The interactive menu is a key part of discovery and its pursuit of an intuitive, user-friendly experience. So we highly encourage you to use this tool as it will provide much guidance and support for any questions or roadblocks you might encounter. Let's exit the help menu and continue the setup. We are now fully set up and a step closer to solving. Before solving, let's review our physics tree and check our fidelity. We can see our physics tree has grown to include multiple conditions. Our material is assigned and the structural loads and supports are defined. You can hover over these conditions to view aspects of them, such as application location and force directions. You can adjust these conditions by editing the values directly on the physics tree or double-clicking and editing on the main tool. Now that we reviewed the physics tree, let's review our fidelity. To do so, navigate towards the Fidelity group in the Simulation tab. Here, you can access the Size Preview and Resolution tools. Turn them both on and we'll be able to evaluate our fidelity. Hover over any geometric feature to look at the voxel being used to represent the geometry. You will be able to see the voxel size, and you can also see the areas in red that are not being captured by the mesh. To increase or decrease the fidelity, navigate towards the bottom of the window under the SID. Here, you will find the fidelity slider. You can slide to set the level of your fidelity, or, while over the slider, you can hit the spacebar and enter the fidelity value manually. The fidelity can be adjusted from 1 to 100. Set the fidelity to a level where you'll capture much of your geometry. As a good rule of thumb, you'll want your voxel size to be equal to or smaller than your smallest length on the model. For this model, it would be the indentations on the side walls. Note that the voxel size will largely depend on your hardware. I am using a 16GB RAM GPU, therefore machines with lower specs will have bigger voxel sizes, while machines with higher specs will have the ability to get smaller voxel sizes.